or heat generated because of recombination losses. So everywhere where you see here this flame, that's where heat is generated, either here in a dark Shockley Hall recombination, the energy gets transferred to heat. Also, if excitons are quenched, the energy can also get transferred to heat. So you need to consider this in a full model. And the last element I'm talking about now, back again to solar cells, is the optical heating. So the thermalization, if you absorb a photon with a higher energy than the band gap, then the energy of the electron, which gets dissipated while going down towards the band gap, that's lost in heat again. So to look into this, I set up a quick model. It's not the full Shockley-Queisser model in SETFOS here, because we still have optical losses, as I was modeling the optic part still with a realistic refractive index. But you get the same trend here with the model when shifting the band gap of the perovskite here, as you can see, for the power conversion efficiency. You can look at the non-absorbed photons which are not absorbed. So the dark green here is transmitted photons through the device which are not absorbed. So you see here there's still some reflection. That's not part of the Shockley-Queisser model, for example. But what we can do now is look at this thermalization part in more detail. So here you can see the same trend where you have higher thermalization the lower the band gap is, because more bigger part of photons that are absorbed are lost in heat, so to say. So we can go into back into the model again and look at this file in more detail. So what I set up here is to go towards the Shockley-Queisser limit. It's just one absorber, and you see here that the injection is perfect level. There are no injection barriers. As I said, I still have a model here, an optical model. So what we're looking at now in the results is directly at the generated power, where we now can split up the heating we saw before and look into the different factors. Now in this simple model, the biggest part, or in general the biggest part, is the thermalization. But even in the simple model with no recombination heating, for example, we see there is this Joule heating which you cannot avoid, as you need to extract the charges. So there will be some fields, some voltage loss and current. So you will have Joule heating, and that's part also of the Shockley-Queisser model. Now it looks like that this Joule heating is like it's not dominating. The whole situation is dominated by the optical heating, by the thermalization. But if we go towards higher band gap, you can see here that these two factors getting closer. So if we have a look at again full model at a higher band gap of 1.6 eV. So you see here again with the transport layer simulated and injection barriers, along with some Shockley-Hall recombination. If we look at the results of this simulation, you can see here that the power that is lost in heat, the heating power, has quite a peculiar shape when looking at just looking through the swept voltage from JSC short circuit towards VOC, and that's because the Joule heating is getting comparable to the thermalization. And just to understand this curve better, if we look at the device current here, the simulated one, if we go from maximum power point here towards short circuit, for example, you extract less and less energy. So if we look at the electrical power with the maximum power point here, if you are at short circuit or at VOC, you don't extract any energy anymore, which means in turn that this energy must be again dissipated in heat. And what's important now is to understand how this heating power is translating to actual cell temperature. So in the model I chose here, you can see that this power translates only to a minor temperature increase here from 300 Kelvin was chosen as rough room temperature environment. But that's because, and now we are looking into some of the parameters of the thermal model, that's because if we go to the boundary condition, which is set up as a convective boundary, so you have airflow, for example, this parameter here, the transfer coefficient of 100 watt per square meter and per Kelvin, represents a very strong airflow. So if we want to have a look into how the temperature changes if we go set a parameter which represents no airflow at all on both sides, then we can run this example, and I have to put here the voltage sweep to only 1.1 volt, otherwise the simulation takes some minutes, which we can't do now in the live view. So with nearly no airflow, you can see here that the temperature effect is now quite drastically compared to the case if we have very strong airflow. So with this model, you can look into this. You could now look into what's happening if we go towards 85 degrees. Of course, you see here there's both air on both sides. If you measure a device, typically you would have on one side a direct contact, so this changes the situation. But this situation would be representative for if you would put a device on contacts and it's somehow surrounded by air, not laying directly on on the heating plate, for example, or some other material. So there is more to this story of a thermal model, but I will not go through all of it. I just want to mention here that the model also considers Thomson-Peltier and Seebeck effects, which are for certain devices very relevant, but as it turns out, these are also relevant to model